Welcome to the lecture third of week 3, that is transformation matrices and robot kinematics. In this lecture, we will discuss about robot frames, forward kinematics of serial chain robot, homogeneous link transformation matrix and DS representation. Basically, these two are parts of doing forward kinematics for a serial chain robot. We will discuss through examples. In the example 1, we will discuss special 3R manipulator, which is a 3 degrees of freedom manipulator. We will discuss on spherical wrist, that again is a 3 DOF manipulator, that is part of the standard industrial robot most of the times, and also on the cobots. In example 3, I will discuss standard 6 DOF industrial serial robot, which is combining both 3 degrees of freedom standard spatial manipulator and spherical wrist. So, let us move ahead with robot frames. As such, robot consists of multiple frames. Robot itself is lying in a workspace, and workspace has got its own frame, which is known as universal frame. You may have multiple robots sitting in the same workspace. Each one of them can be individually addressed with reference to this particular frame. This is universal frame. You can have first robot sitting here, second robot, third robot, fourth robot. So, the base of each robot can be addressed with respect to this frame. Now, the robot itself has a frame. Those were this. Okay. So, this robot frame has all the links and the joints and its end effector. Each and every parameters are represented with respect to this frame, because this frame is attached to the ground where the whole of the robot is mounted. Normally, it is sitting at the bottom of the robot at its center, okay, about which you measure the end effector position, where all the joints are located. Okay. So, that is known as a robot frame or robot base frame. And you also have a hand frame. Where is your hand frame? Hand frame comes here, on which you put your tool. Okay. So, that is just like the flange of the robot on which you mount your tool. So, that is also known as a hand frame. You have a part frame, that is any object which is lying in the workspace may have its own frame, that is also known as a object which the robot is handling. Okay. So, this has its own frame. This may be a solid object. So, that frame can represent the position and orientation of the object, okay, with respect to the universal frame, or it can also be with respect to the robot frame. Okay. And the final frame is the end effector frame, that is at the tip of the tool. Okay. Let us say if it is a welding tool, it becomes the tip of the welding electrode which actually does the job. So, that is the end effector frame. Apart from these, there may be many other frames which are helping us to do the kinematics, dynamics, controls and many other things. One such frame is a joint frame. This is the axis about which the links of the robot move. Okay, that is known as joint frame. So, we will talk each one of them precisely when it comes. So, let us begin with forward kinematics of standard serial chain robot. What is a serial chain? Serial chain robots are made in a way that it has a fixed base and links come one after the other till it terminates. In between, you have joints which connect two consecutive links. So, you have a link, you have a joint, you have a link, you have a joint, and finally, it has the final end effector which finally terminates, or it may hold something. So, forward kinematics problem of a serial chain robot is defined as, given the individual joint displacements or angles, we solve for the end effector pose. The pose here I would mean position and orientation. So, let us say this is a robot, okay, this orange color one. So, it is a standard serial chain robot. So, it has a fixed base here and it has a end effector that comes here. So that actually does the job, and you have a link, you have a joint, you have a link, you have a joint, link, joint, link, joint, link, joint, and finally it terminates. So it is a serial chain. Okay. So the problem here is you have to find the end effector position, and joint angles are known. You also know the dimensions of each link. So you know the link lengths, okay, L1, L2, L3 and so on and so forth. You know the link dimensions, you know the geometry of the link, okay, where all the joints are placed. So knowing the joint angles theta 1, theta 2, theta 3, each joint angle you can calculate the end effector position. So doing this problem is known as a forward kinematics problem. So steps for doing forward kinematics is as follows. Number 1, we'll understand the links, the joints and different parameters that define them. Number 2 would be placing the Denavit-Hartenberg, commonly known as DH frames. We'll place those frames, we'll learn what is that first, and we'll place them while we do forward kinematics of few of our examples. We'll create a parameter table, which is commonly again known as DS table or Denavit-Hartenberg parameter table, in short DS table. Fourth one would be forming the individual link transformation matrix. We'll form link transformation matrix that would transform the points from start of the link to the end of the link. We'll perform the direct kinematics or forward kinematics of the robot. So these are the steps for doing forward kinematics. So let us begin with link, joint and their parameters. We'll define that. This basically defines the structure of the link, its placement on the robot structure, okay, not just the link itself, it also defines where and how it is placed on the robot structure. So a link basically should have a shape which is something like this, as given here. It starts with a joint here and it terminates with another joint. So the starting joint, if that joint moves, whole of the link moves, okay, and this link ends with a joint again which connects the another link that comes next, okay. So there is a joint axis here, there is a joint axis here. First one is known as a proximal end, other one is known as a distal end, okay, and this is your link, okay. So now you find the link here in this figure, okay, this is your link, we call it link I, and prior to that you have a link I minus 1, okay. So this is your serial chain structure. So the joint axis about which link I moves is attached to Zi minus 1. So this is the frame or the axis of the frame which is attached to the link I minus 1 about which link I moves. Over here I have shown rotation, but it can also be a prismatic joint where it moves in a linear way, okay. Now the parameters goes as, the first parameter is known as joint offset. Where is it? Let us say you have a link axis that goes like this, the second link also has an axis that goes like this, okay. So these are the link axes, and the axis which is here is the axis about which link I rotates with respect to link I minus 1 about the axis Zi minus 1. So this is the axis Zi minus 1, okay. So the common normal, okay, so these two are the points where it intersects the x axis. So this is your xi minus 1, this is your xi. So the points where it intersects xi minus 1 and xi, so the distance between them is known as offset. So this is your distance which I am talking about. So this is di. So it is commonly represented as di, it is the distance from the origin of I minus 1 coordinate frame OI minus 1 to the intersection of ZI with XI axis, that is here along, and the distance is measured along ZI minus 1 axis, that is like this. So, this is the direction where you have to measure it. Okay. So, this is the first parameter. Now, the next parameter, that is known as the joint angle. For revolute joint, it is joint angle. So, theta I is the joint angle from xi minus 1. So, you have xi minus 1 and xi. Okay. So, this is xi minus 1 and xi about zi minus 1. So, this is the angle. So, it should be as per right hand thumb rule. Okay. So, this is the xi and xi minus 1 angle between those two measured in a plane which is perpendicular to the axis zi minus 1. So, that gives you the joint angle. So, the projection of that, when you look from the top, this is the angle, that is theta I. The third parameter is link length. So, this link itself rotates about zi minus 1. It terminates with the frame which is sitting here with z axis again along the motion axis for the next link that will come here. Okay. So, this is zi and this is zi minus 1. So, the distance between them, if you draw a common normal to these two, so that would create a xi axis, okay, that is known as xi axis, that comes here. So, that is a common normal to zi minus 1 and zi, okay, and distance between them is the link length and commonly known as ai. Okay. Ai is the offset from the intersection of zi minus 1 axis with the xi axis to the origin of ith frame OI along xi axis. Okay. So, what is twist? Twist is given by alpha I. Alpha I is the offset angle from zi minus 1 to zi. If you look from here, okay, there is a twist angle. So, that is measured about xi axis, okay, that is measured about xi axis from zi minus 1 to zi. Looking from here, it is alpha I. So, it is mentioned over here, that is alpha I. Okay. So, these are the 4 parameters d, theta, a, alpha. Okay. I have just summarized it here. Okay. So, ai and alpha I, that is link length and link twist, because it is a solid link. So, this defines the structure of the link. This is not going to change with time. Okay. So, what changes is di and theta I. So, di in case of prismatic joint, di becomes the moving axis, okay, and in case of revolute joint, theta I is the moving axis displacement. So, these two are the displacement which define the relative position of the neighboring link. Okay. So, these two may vary, but in case of revolute jointed robot, which most of the cobots are, only theta I is the variable, di is fixed. So, in that case, link length, link twist as well as di is fixed, only theta will vary. Okay. Now, let us find out the transformation that takes you from OI minus 1 to OI, that is from the frame which is sitting over here to frame which is here, that is this link itself sits on this frame and it terminates with the next frame. So, OI minus 1 and OI, okay, where OI finally will have the next link in series, or it may be the final joint in case of the last link. So, that becomes the terminating frame. Okay. So, we need to know the transformation that takes you from this point to this point. So, the first one will do is translation along ZI axis. Okay. So, let me draw it here. So, if this is your xi minus 1, so this is your xi. Okay. So, this is the distance. So, this is your di. So, it is translation along zi minus 1 that takes you from xi minus 1 to xi. Okay. So, that distance. So, it is a displacement along zi axis by a distance di. Next one would be rotate about zi minus 1 axis by an angle theta I to align xi minus 1 to xi axis. So, if it starts from here till here, okay. So, from here to here, that is rotation about zi minus 1 axis starting from xi minus 1 to xi by an angle theta I. So, this is a rotation transformation about z axis by an angle theta. The fourth one is again translation along xi axis from zi minus 1 to zi. So, if this is your zi minus 1, this is your zi. So, this is the distance it is telling. So, this is from here to here, that is the link length it along xi axis. Link length is measured along xi axis. From here till here is the translation about xi axis by a distance ai, that is the third transformation. The final one is rotate about xi axis. This is rotation about xi axis, okay, that takes zi minus 1 to zi. Okay. So, if you look from here, so it is rotation about xi axis by an angle alpha I that would take zi minus 1 to zi. So, final transformation is a rotation transformation about xi axis by an angle alpha. So, 4 transformations are there. Let me summarize. So, it is the first one is displacement along zi minus 1 axis by a distance di. The second one is rotation about zi minus 1 axis by an angle theta. Third one is displacement along xi axis by a distance ai. The final one is rotation about xi axis by an angle alpha I. 4 are there. So, 4 consecutive transformation can be written like this 1, 2, 3 and 4. So, this is translation about zi minus 1 by a distance di, rotation about zi minus 1 by an angle theta I, translation about xi by a distance ai, this is rotation about xi by an angle alpha I. So, these are the transformation matrices that we have studied in the last lecture. So, these are the 4s and they are you see they are applied one after the other with respect to the previous frame, that is relative transformation. So, this time it would be post multiplication. In order to get the final transformation that takes you from I minus 1th frame to ith frame, you do post multiplication, that is 1, 2, 3 and 4. If you multiply them all together, you get the link transformation matrix. This will take you from I minus 1th frame to ith frame. Okay. So, this is a combined transformation for all the translations and rotations that defines the link shape, that is apart from theta I that defines the link position with respect to the previous link, remaining are di, alpha I and ai, that is giving you the link shape, okay, and its structure. Note here ai minus 1 with respect to ai is equal to inverse of I with respect to I minus 1. Next is theta I is the only variable for revolute joint. In case of prismatic joint, variable is di and ai, that is link length, becomes equal to 0. If you put these values to the previous ai minus 1 ai transformation, it becomes this. Okay. So, this can also transform the point which was at pi minus 1. If you multiply with this transformation matrix, it takes you to the next frame. Concatenating them, let us say you have first link, you have second link, you have third link, and so on so forth. So, A0, A1, A2, if there are multiple links like that, so one by one each of these transformation will take you from this to this. This takes you from this to this. This takes you from this to this. Finally, it takes up like this. So, if you have to go from here to here, you multiply them together. Okay. So, that is what it is telling. So, if you have to do forward kinematics for a robot, you have to reach to the end effector from the base. Each link has its own transformation matrix. Okay. So, what you will do? You will multiply them together and finally get the state of the end effector. So, final matrix that will come out of multiplying all of them, link transformation matrix, will give you the final matrix 4 cross 4 homogeneous transformation matrix, which finally gives you the state of the last frame, that is also known as the end effector frame. Now, I will be using joint symbol like this for representing any revolute joint, and a kind of symbol which is like a cube to represent all my prismatic joint. In case of cobot, there is no prismatic joint because that needs to be backdrivable. There are many other things to be discussed, we will be doing it. So, it does not allow a prismatic joint in a standard cobot, okay, because they are not necessarily, they are not easily backdrivable, okay, but it is not that it is not possible at all. So, most of the time we will be discussing on revolute joint in this course, okay. So, we will use this kinematic representation to represent a joint which is a revolute joint and whole of the structure with sticks, okay, instead of drawing it in a complex shape geometrically. So, we can directly draw using this. So, let us summarize Dennawart-Hurdenburg representation here. So, it is a matrix method for systematic establishment of link coordinate system of an articulated chain. Okay, this results in 4 cross 4 homogeneous transformation matrix ai minus 1 ai that relates the ith link to I minus 1th coordinate system. So, this frame is fitted at the end of I minus 1th link. Okay. The end effector may be expressed with respect to the base 0. Finally, when you take product of all those link transformation matrix, it takes you from the base frame, that is 0 to the end effector. Okay. When a joint activates, link I will move with respect to link I minus 1. Ith coordinate system with zi moves along with the link I. Okay. So, every link I will end with frame I and that moves along with the link I. Okay. So, let us assign DH frame and do forward kinematics now. So, we will do it for 3R spatial manipulator. How does it work? Let us just see the motion here. Okay, now let us see the video. How is this structure? So, this is moving joint 1 that moves link 1, link 2 and link 3. Now, joint 2 is moved, that moves link 2 and 3 only. Whenever joint 1 moves, it moves joint link 1 about its own axis, so it may not be that noticeable here. Link 2 and 3 are moving. This is only link 3 is moving. So joint 3 is in action. Okay. This is to make you very clear how does this 3R spatial manipulator look like. The moving joint 1, 2 and 3 simultaneously will move whole of the robot. Okay. So moving joint 2 and 3 simultaneously. Now I have moved them all and put the arm in static position and moved joint 1 only, so as to show you that this is a plane on which link 2 and 3 lies, and that plane moves about axis 1. Okay. So this is how it is. Okay. So let us do the DH frames first. We will put all the DH frames here. Okay. So starting from here, so assign Z0 here, Z0 axis along the axis of first joint. So Z0 comes here, this is Z0 about which link 1 will move. Okay. Now appropriately assign x0 and y0. So x0 is put here and y0 is put here, z0 was here. Okay. This is your link 1. Now assign z1 axis along the axis of I plus 1th joint. Assign zi axis along the axis of I plus 1th joint. So likewise you keep on putting all the z axis. So this was your z0. At the end of link 1 you have next z1. Okay, this is the frame which moves along with link 1, okay, when it rotates about its axis, and similarly z1 is the axis of rotation for link 2. Link 2 terminates with the frame with z2 over here. Similarly this is link 3, this finally terminates with the frame with z3 over here. Okay. This is how all the z axes are placed. Okay. This is your end effector, this is the robot base. Once all the z axes are placed, place xi axis which is located along the common normal to zi minus 1 and zi. So if this is your z0 and this is your z1, so common normal to that is, okay, so this is your x1. Okay. Similarly, as because this is your z2, so common normal will be making this x2, and the last one, as because this was your z3, so this becomes my x3. Now that I know all x and z, I can quickly get my y axes. Okay. So y axis is simply obtained by z cross x. Okay. So y can be quickly drawn here. These are my y axis. So these were my z axis. Okay. So these were your x axis, got it. This is how you placed all the x, y and z axis, and this was your initial x0, this is your y0. Okay. So this is how all the frames are placed. So di is equal to distance from origin of I minus 1th coordinate system to the point where xi intersects zi minus 1. So over here you have distance measured along Zi minus 1, this is your Zi minus 1 till Zi, okay, and how much is that? So this distance is your di, okay. So over here it is first link, so it is d1, okay. So this is present here, okay, but you see there is no other di, there is no distance measured along z axis across any of the other links. For link 2 and link 3, that is not there, okay. Now set theta I is equal to the rotation about axis zi minus 1. So this is your zi minus 1, this is your theta 1, okay, that is first joint angle. So if this was your z, this is theta 2, this is your z, this is theta 3. So these are the joint angles. So over here all three were revolute joints. So theta I is rotation about the axis zi minus 1, okay. So this was your z0, so this is theta 1, this is z1, theta 2, z2, theta 3, this is z3, and there is no further link here, okay. So now ai, that is equal to the distance from zi minus 1 axis to zi axis measured along xi. This is actually the link length, okay. So this is your z0, this was your z1. You see there is no distance between them. Both the zi's, they intersect at this point. So that link length a1 becomes equal to 0. There is no distance between them. For next one, z1 and z2, there is a common normal, and you see this is your a2, okay. From here to here again you have common normal, okay, that is x3 coming here, and this is your a3, okay. So these two are link length, and this was your joint offset that takes you from O0 to O1, okay. So alpha I is equal to rotation about xi axis that needed to rotate from zi minus 1 to zi. So there is no angle between z1, z2, z2 and z3, but when you look at this one, this is z0 and z1, if you measure about x1, you see z0 comes from this to this. So you have to follow right hand thumb rule. So it is about x1 you are measuring, so it is plus 90 degree. It can be taken from z0 to z1. Got it? So this becomes my alpha 1. So it is alpha 1. And for others, there is no angle between the z axis. So z1 is parallel to z2, z2 is parallel to z3 at all times. So there is no twist, okay, about the x axis. So x axis is where here, so there is no twist about that, okay. So link twist is missing for link 2 and 3. So finally you keep doing this, repeat till the last joint. You have to keep doing this for all the links, okay. Assign Zn along Zn minus 1. So last, just because this is Zn minus 1, this was Z2, so last frame will be Z3, and this is normally kept parallel to this, okay. Okay. So I have already shown you the video here, that is this one, how it is working. So this is all the parameters I have summarized here. So D1 is placed here, A2 and A3 is here, joint angles are theta 1, theta 2 and theta 3, okay, and finally all the frames are put right here, okay. So I will switch it off here, the video. Now the DH parameter table will tabulate as link 1, so that is for the first link, okay. So, you have parameters a1 is equal to 0, there is no distance between z0 and z1. So, that made a1 equal to 0. Alpha 1 is angle between z0 and z1 measured about x1. So, it came to 90 degree. d1 is the distance measured along z0 from this frame to this frame. Okay, that is d1, and theta 1 is the joint variable. Next one is distance between z1 and z2 measured along x. So, that is link length. There is no angle between z1 and z2 measured along x1. So, twist is 0. There is no distance because both the joints they are in a plane. So, there is no again distance travelled along z axis. Okay. So, that made joint offset equal to 0, and theta 2 is the joint variable. And the final one similarly a3 is distance between z2 and z3, okay, from here to here measured along x3. So, that is a3. Twist is 0 again, d is 0 again, theta 3 is the joint variable. Okay. So, this is how whole of the DH parameters are complete, and we tabulated it in a DH parameter table. Okay. So, we will use the link transformation matrix here, ai minus 1 ai, that is will take you from this to this. So, a 1 0 would mean it is taking you from 0 to 1th frame. Similarly, a 2 1 would mean it takes you from this to this frame, okay, and the final one would take you from here to here, that is a3 2. Okay. So, there are 3 link transformation matrix, and you have to substitute each one of them to this to get a0 1, a2 3, a1 2, all the 3 matrices will be obtained, that is known as link transformation matrix. So, these are those. Okay. So, if I take product of all those, I can quickly get the state of the end effector frame here. What it says, because it is a state, it says the position over here, that is the position of the end effector with respect to O, that is the base frame, robot's base frame, and these 3 would tell me the orientation of the end effector with respect to the base frame. Is it that trivial to validate it as well? We will try doing it now. So, let us do it. Okay. So, now quickly comparing the values here, whether this point gives me, that is the end effector point, that is x, y, z, gives the location over here in the homogeneous transformation matrix. So, you see just by taking trigonometrical projections here and adding the components, you can directly get the values. Okay. So, let me just check, see, this is your link length a2, a3, theta 2, theta 3. There will be 2 components here, horizontal component like this. So, you see this arm has link 2 and link 3 that is lying in a plane. Okay. So, this is that plane. So, there are 2 projections. The horizontal one would be a2 cosine theta 2 plus a3 cosine theta 2 plus theta 3. Theta 2 3 would mean theta 2 plus theta 3. Okay. So, if we sum this distance, that is from here to here and from here to here, that is quickly this one and this one. So, this becomes my horizontal component. Now, the vertical component is this, that is a2 sin theta 2 plus a2 sin theta 2 plus theta 3. So, those two are the horizontal and vertical components. Okay. So, that is quite trivial here. Okay. Now, this d1 is equal to d1. So, now you can quickly get at least the vertical distance, that is the z coordinate here. So you see it is available here, that is d1 plus this plus this. So overall you got till this. Got it? So that is validated. Now as because this is the horizontal projection, so x and y would be simply component of this along x and along y. So that gives you this, that is x, this is y, and this was your z, whole of this. Got it? So this is your z. So you see you can quickly validate. So this is your end effector position. Can we also calculate the orientation here? Okay, let me just check that. Is it possible as well? So let us go back to previous figure here. So over here what you found, it is A01. Okay, what does it mean? It is transforming from, this is link transformation matrix 1, it takes you from this point to this point. Let us look it from the top. How does it look like? It tells you x0 here, y0 here. Okay. What about the first frame? It tells you, if you look from the top, your z1 is here and x1 is here. Okay, that is rotated by an angle theta 1. Okay, so now you look at the projections. Okay, what do you see? x1, projection of x1 along x0, along y0, along z0. Okay, so x1 along x0 would be cosine theta 1, x1 along y will be sine a theta 1, x1 along z, z is perpendicular to this plane, so it becomes equal to 0. So quite clear. Now what about this column, that is for z? So this again is making an angle theta 1. Okay, so this time you see projection along x0 for z1 would be sine theta 1. Okay, for projection along y for z1 would be minus cosine theta 1. Mind it, all the vectors here are x0, y0, z0, x1, y1, z1, they are all unit vectors. So this is here, and then finally it is in a plane, so that makes it 0. What about z axis? Okay, z axis projections. Okay, along z0 y1 is always lying, so you see a continuous projection of y along z as 1, other two projection would become equal to 0. So this is the way you can validate each one of these matrices. Okay, so if you have to validate this, you have to see this on this. If you have to validate this, you have to see this on this. Okay, so those are these orientation matrices. Okay, definitely this gives you the relative position as well. Okay, that we have anyway verified over here, so we won't do it again. So the final one would be this one. So product of all these basically gives you this as orientation. What does it tell you? That is the projection of last frame x, y and z along the global base frame, that is x, y and z, projection of these. So this is projection of end effector along x, along y and along z. Okay, and this is your position. So you can validate each one of them. Okay, you can validate the position also, or you can just put the value for a particular value and trigonometrically you can calculate it. Okay, it would not be always possible, at least for higher degree of freedom robot. Okay, okay, now let us move ahead. We'll talk about spherical wrist. Where have you seen it? Let me just show you once again here. So if this is a robot, okay, this is a robot here, it terminates with a spherical wrist. So first three axes basically would take you to any position, that is xyz position, as you have seen in the previous example. Okay, this is a positioning robot which takes this end effector to a position. The next one would be to orient it. Okay, now I have reached there, I'll orient it, align it with the object and do some valuable work. To align it, you need further 3 rotations, as you have seen in Euler angle systems earlier. Okay, so this is one of them. It is roll pitch yaw system. So you see what it does basically. The axis 4 is like this, axis 5 can take you like this, and finally axis 6 is the axis that moves the flange. Finally this attaches the tool. This is where the grippers are attached. So if I remove all the frames here, you can see that. So this is axis 4, this is axis 5 and axis 6. All the 3 axes are intersecting at a point which is known as spherical wrist. Okay, so all the 3 axes, they intersect over here. So axis 4, axis 5 and axis 6, they intersect here. This is what I am talking about. So these 3 axes would finally orient this to align it with the object which this robot needs to handle. Okay, axis 1, 2 and 3, that takes you to a position. Axis 4, 5 and 6 actually takes you to a particular orientation. So this is your displacement along axis 4, this is your displacement along axis 5, and finally you have, that is your axis 6. Okay, so these motions are along. So if it is theta 4, it is measured about the previous frame, that is Z3. Similarly, if it is theta 5, moves along theta 4, theta 6, it moves along Z5. Okay, so all the 3 axes are intersecting here. Okay, so that becomes my wrist center point. Okay, now let us do the DH parameters for this. This can be quickly found as, so you have seen it here in the previous case. You have to attach this wrist on top of the previous one. So that is the reason I started with 4. 1 to 3 is already over in the last example. Okay, so now this is your link 4. So fourth link comes and it ends here with the final frame Z4. Z4 actually, yeah, fifth link is moving about Z4. Okay, and Z5 is here, that actually moves the 6th link here, and finally it ends at the end effector over here. Let me just recapitulate this. You see, this is your 4th one. Okay, and you have 5th one, 5th theta 5, and finally this is your theta 6. Okay, so you start with 0 frame, 1, 2, 3, 4, 5 and 6, that is the last frame. So if you just can see this, because there is no distance between Z3 and Z4, so that makes A4 equal to 0. Angle between them measured about x is minus 90. Offset, again because it is intersecting, there is no offset, there is no distance which is traveled along z axis. So for 5th one, for link 5, what you see here, it is AI becoming equal to 0. Okay, because there is no distance between Z4 and Z5. Okay, so that makes it 0, and coming from Z4 to Z5, it is plus 90 degree, that is measured along this. So that is plus 90 degree, and DI, because both the axes are intersecting. Okay, again there is no distance traveled along z axis here, so that makes this offset equal to 0, and theta 5 is the joint angle, that is the joint variable here. Okay, again the 6th one, that is the 6th link, what you see here, AI, that is distance traveled between Z5 and Z6 because they both of them are collinear. Okay. So, there is no distance between them, that is measured along x axis. So, that makes A6 equal to 0. Okay. There is both the axes are parallel. So, there is no twist angle here, and D6 is the distance from here to here, that is till the tip. So, that is D6, that is the distance travelled along this axis, okay, from wrist center point to the end effector. So, that is D6, and finally, theta 6 is the joint variable. So, this makes the complete DS parameter table for the spherical wrist. Okay. If you put them in transformation matrix, that is link transformation matrix AI I minus 1 individually, so you get A3 to 4, A4 to 5 and A5 to 6. If you take product of them, this gives you the complete pose of the end effector with respect to the third frame, because you see it is 3 here, from 3 to 4, 4 to 5, 5 to 6, take product, it gives you from 3 to 6. So from the third frame till the end effector frame, so this is the transformation. This again can be validated, but it is not that trivial. This gives you the position, at least this may be verified. So that is the wrist of the robot. Okay. So now if you put them together, let me just put it here. So this is your spherical wrist, and prior to that you had thread of arm, okay, that is a special arm which was here right till here. Okay. So that was a special arm. If I put this on top of this, it becomes a spherical wrist on top of 3R special manipulator, it becomes a 6 degrees of freedom arm. So there are many such arms which are there. One of them is KUKA LBR IISY, Kinova Gen 3, DLR SARA, Stably TX3 and many similar arms are there. If you set them at home position, it becomes a robot which is in a straight line. Okay. So that is the beauty of it. But yes, most of the industrial robots, they have the base offset. That means the first axis and the second axis, there is some distance between them. First one is a vertical axis, the next one is the horizontal axis, the distance between them exists. Okay. That is to make it little forward so as to do most of the forward tasks, okay, the tasks which are in front of the robot. But in case of cobot, we tend to put them in lines because it may have a symmetrical workspace all around. If you tabulate them in DS parameter, it becomes very much like this. Okay. So you have first 3 for the 3R special robot, that is the positioning robot, and rest one is for 3R spherical wrist. Okay. So that comes here. Only difference that comes here is the axis. So if you look carefully, the last link had Z like this, now it is like this. Others are exactly the same because now it has a axis that comes like this. So now I have to put Z3 like this. Okay. So that makes it the little bit modification in the DS table, otherwise it is all the same. So you see Z3 is now like this. So Z3 and Z4 is here and Z5 is here. Okay. Finally Z6 is the last frame. Okay. So that makes it complete. Okay. So when you do put all the DS parameters to the link transformation matrix and take the product, you should be getting the end effector pose, that is the position and orientation, that is homogeneous transformation matrix that would represent the state of this end effector frame. So it gives you this as well as the orientation of the frame which is sitting here with respect to the robot base. For all other cobots, there is no intersecting axes in the wrist. Most of the cobots, you see, there are only two axes which are intersecting next to next. There is never a place where all the three axes are intersecting. That is what I mean normally for UR arm and many other similar arms. Okay, we will talk about that later. So yes, you can always have some further materials that are here in my course, Industrial Robotics Theories for Implementation. Okay, lecture 18, 19 and 20 you can refer. Lecture 20 discusses Yaskawa GP12 robot. Quite lot of cobots, they are also of this type, and their forward kinematics can be done in a similar way. Okay. Others are 2 DOF, 3 DOF robots, 3 DOF cylindrical robot, wrist again is discussed here. So, 3 DOF over spherical wrist is there also, SCARA robot is there. So, you can look at these. This is the link for the course. That is all for this lecture. Thanks a lot. In the next lecture, I will discuss forward kinematics of industrial cobots.